Okay. So this theory says if this is a particle, okay, then there are three forces will act on this particle. One is gravitational force Fg, another is drag force Fd, and the third force, which is also in opposite direction to Fd, is buoyancy, force of due to buoyancy, B. I'm sorry. Okay. So at terminal velocity, when the particle is settling with terminal velocity Vs, in that situation, this Fg should be equal to Fb plus Fd. Can you see the whiteboard? Is that whiteboard visible? Hello, Kunal Gupta.
Yes, ma'am. Yes,
Ma'am,
ma'am.
what is
Okay.
visible? Yes.
It is visible.
What? Okay. Okay. So Fg means uh, gravitational force, which will be equal to mass into acceleration due to gravity, right? M into G. And mass of particle can be given by the volume, right? Volume of particle multiplied by what? Density of particle, right? Into G, right? Volume can be given by, for a spherical particle, we can write the volume as pi by 6 into dp cube, right? Into rho p is the density, g is the gravitational acceleration. Okay. Then Fb, force due to buoyancy, can be given by again the same mass multiplied by G. That is mass of water replaced, which is like again particles volume multiplied by rho W, right? Because this is the water which will be replaced by the particle will have the buoyancy force, right, on particle into G. So again this will become pi by 6 into dp cube, right, multiplied by rho W into G. Okay. Then what is Fd? Fd, Newton gives Fd as Cd, which is drag force, multiplied by cross-sectional area of the particle, multiplied by, let me just see, I do not want to write anything wrong. Okay. Multiplied by density rho W, okay, because drag is because of the water around the particle, into Vs square divided by 2. Okay, this is Fd. Now if you will solve this, you can do it like this: Fd is equal to Fg minus Fb is equal to, so if you equate this, this will become equal to pi by 6 dp cube into rho p minus rho w into g. Is that correct? Right? And then you can solve this whole thing by putting a is equal to pi by 4 into dp cube, cross sectional area of the dp square, I'm sorry, dp square, cross sectional area of the particle. If you will equate this, you will get a final formula Vs. I'm just writing the final formula. You can solve it. I think I have told almost everything. It's easy to solve now. You will get the final formula 4 by 3 into G into D, which is dP, into capital G minus 1, where capital G is equal to rho S solid or rho P, whatever, rho P upon rho W. Okay, rho P, this is specific gravity of particle. Okay, the density of particle upon density of water into this will be like this, and then divided by CD. Okay, whole raised to half. Okay, this is the final formula you will get after equating everything and putting A is equal to pi by 4 into dp cube. Right? Now, hello? Hello? Nand Krishna, do you want to say something? Otherwise, mute your mic. Okay. Now, this is the formula which we can use for VS. Now, there are conditions. CD, which is actually CD, depends upon Reynolds number. Okay. And there could be three conditions. One is laminar flow. Second would be transitional flow. Right? And third would be turbulent. Okay, so for that I will just rub this board and we will go ahead with Reynolds number. CD, actually not Reynolds number, CD. Okay, the Reynolds number, the drag coefficient CD is drag coefficient, and that is given by 24 upon RE for laminar flow. Okay, and if you will put this value, then you will have this formula in this way: Vs is equal to G into D square, which is dP square, into capital G minus 1 upon 18. Okay, you can put this 24 by RE, and you can find out, and there should be nu over here. 1 minute. Yes. So there should be nu. Nu is kinematic viscosity. Viscosity of water. Okay. So nu will be on the bottom, and this, if you will put, because RE can be considered as rho D into Vs dP into Vs upon nu. Okay. So putting that here, 24 divided by RE will go up, right? In earlier formula, then you will get this. So you can derive it. It's not a big thing. Okay. So now this is one formula. This formula of Vs is applicable when RE is less than 1.0. This is known as Stokes law. This is Stokes law. And this is applicable when RE is less than 1.0. Always remember it. Okay. Now, when there is a like temperature of water is given, say if temperature is not normal temperature, or means or you can say, if we want to consider the temperature also, because that will affect the velocity, then there is another formula is given. Just please note down the formula, because I think this other formula is not given in PPT. Okay, I'm writing the formula when temperature is given. Okay, and yeah, so Vs is equal to 418 into G minus 1 into D square, which is dP again. Okay, 3T. T is the temperature in Kelvin, plus 70 divided by 100. Okay, this is for dP is less than 1 point, no, point 1, I'm sorry, 0.1 millimeter. Okay, 0.1 millimeter. T टेम्परेचर सेंटीग्रेड में नहीं होना चाहिए. To T, okay, T is the temperature in degree centigrade, not in Kelvin. Small t देना चाहिए था उसको. So T is equal to temperature, water temperature of water in degree centigrade. Okay, always remember that. Okay, then this is one formula. The other formula which is given by Newton is when D is greater than 1.0 millimeter. Okay, then Vs can be given by 1.8 into small g into D multiplied by capital G minus 1. Okay, this is another formula for D is greater than 1 mm, and when D is actually between 0.1 mm to 1.0 mm. Then Hazen has given one formula. This is Newton's formula. Now, for this case, Hazen has given formula, Hazen. And that formula is similar to the earlier one. Vs is equal to 418 into G minus 1. Only there is a dP, not dP square. That is the only change. This is 3T plus 70 upon 100. So it is easy to remember these formulas, but you will have open book exam. You can see the notes also. There is not much difference between two formula, but you need to remember the cases. Okay. So this is how the sedimentation theory works for settling particles. Okay. Now I'm sharing my slides again. Have you noted down? Have you noted down the formula? Note down the formula, okay?
Okay, ma'am.
I will give you just few minutes to note it down. Okay.
Could you just
Yes.
scroll down and
Your voice is not clear, Hetal.
never mind.
It's not clear. Okay. Okay. So CD is given by here you can see the CD. I have written CD. Can you see the slides now?
Yes, ma'am.
Okay. Okay, so here you can see a graph on the left hand side. In Stokes region, which is like when Reynolds number is less than 1, right? The CD can be given by 24 upon RE. In transition region, when Reynolds number is between 1 to 1000, the CD is given by 24 upon RE plus 3 upon under root RE plus 0.34. Okay. And for Reynolds number greater than 1000, which is in turbulent zone, the CD become almost constant 0.4 or 0.44. Okay. So this is how you can use the drag coefficient. Means either just use the formula and calculate the drag coefficient, or you can also use the graph. So here the formula for different cases are written. Only the formula for transition flow I have not written, because there are 2-3 formula. As I said, like one is when temperature, when we consider the temperature. So that is not written here. Otherwise, all other formulae are written. You can use those formulae as per your case. This is one of the example. What you can do, it's already solved example. You can go through it. I will just read the question. Consider two solid sphere P and Q, each of density 8 gram per centimeter cube and diameter 1 centimeter and zero point 0.5 centimeter. That means 10 millimeter and 5 millimeter, okay, respectively. Sphere P is dropped into a liquid of density 0.8 gram per centimeter cube. So the particles are heavier than the liquid, and viscosity mu is equal to 3 sphere Q is dropped into liquid of density 1.6 gram per centimeter cube, and viscosity mu is equal to this much, right? Determine the ratio of terminal velocities of P and Q. So actually, you don't have to. You have to do to take the ratio of velocity, terminal velocity of particle P and Q. So that is done here, and it's very easy to understand. You can just go through it. If you don't understand it, then let me know. We will see in the next class. Okay, now what are the type of settling that happens in the tank? Uh, See, this is a kind of theory to explain the settling process. It is not like somebody has seen it, and like it can be observable also. You can see that if you in laboratory we use the transparent column and we put the wastewater in that, and we observe this phenomena in laboratory. However, I'm just saying that this is how the settling process can be explained, or the mechanism of settling can be explained, you can say. So this discrete settling, this is the settling we think that happens when the particles are inert, they are not collide with each other. Individual particle has enough mass or gravity to settle down. Therefore, it's a kind of settling of individual particle or discrete particle. Discrete particle, that as I said, it's an inert particle. It's heavier than the liquid, and they settle down individually. They do not coagulate with other particles. So that is discrete settling. Flocculent settling, when the particles are not heavy enough, they are light in weight. They especially in case of coagulation process, when we put the coagulant in the water, what happens? For example, in case of alum or magnesium related coagulant, it forms aluminum hydroxide. Aluminum hydroxide flocks are light in weight. Okay, so they generally collide with each other. While they are individual, they will not have enough mass. They will not settle down. They will float in the water. However, when they come together and make a flock, the flock becomes heavier than the water, and then they start settling down. Okay, so but this kind of settling we generally say happens or prevails when the particle concentration is less than 1000 mg per liter. Okay, so that is basically for in coagulation process or when bioflocks are there. Bioflocks means what? Bacterial mass. Okay, so in case of wastewater, when we there is a process called activated sludge process. When we actually provide the sludge or the seed or bacterial seed to the water, so that the bacteria will grow inside the tank and they consume the organic matter quickly, or then that during that process what happens, the bacteria grows as well as there is a decay phase of the bacteria. So that solid which contains the bacteria called biofloc. Okay, so, chemical flock as well as bioflock, when the concentration is low as 1000 mg per liter, we think that the kind of settling which happens can be defined as a flocculent settling. So this is the illustrative figure for settling. You can see the clear water on the top. The discrete particle, which is individual particle, is settling down. That is discrete settling. The flocculent settling, when the 3, 4 or 5 particle, whatever the number of particles, they coagulate with each other and they make a flock and then they settle down. That is the flocculent settling. Other two type of settlings are written here. Type 3, which is hindered or zone settling, that happens when the concentration of particle is high. It's a greater than 1000 mg per liter. In that case, what will happen? The particle will hinder or they will actually affect the velocity or the settling profile of each other. Okay. So in that case, settling of the particle result in significant upward displacement of water. The whole mass of the particle settle as a unit or zone. Okay, so this you can visualize it as a large flock settling down together. A large kind of sheet of flocks, they are settling down together. So the concentration is very high. The particle behavior will not be individual. Like the particle will affect each other. The settling of particle will be affected by each other. Okay, so in that case, this is called as hindered settling. The type of settling is applicable to concentrated suspension as are found in secondary sedimentation tanks are following ASP. ASP is activated sludge process. So as I said, in activated sludge process, what happens? The raw sewage means wastewater, is mixed with a fraction of sludge from the secondary settling tank, which has enough amount of bacteria to provide the bacterial growth in sediment in activated sludge tank. So there are two tanks. One is first tank, which is also known as aeration tank, where air is provided to speed up the bacterial growth and bacterial activity. The bacteria consumes the organic matter. So ASP has two units. One first unit is actually aeration tank, and second unit is secondary settling tank. Okay, so the fraction of sludge from secondary settling tank is actually recirculated in aeration tank for to you can say accelerate the growth of bacteria and biological process in aeration tank. So in that case, the settling happens in secondary settling tank is kind of hindered settling because the concentration of solid is very high. Compression settling, this is the kind of settling where the further the concentration of solid is very like much more higher than even the hindered settling. Okay, so what happens? The kind of blanket of the whole sludge gets settled down, and the water between the pores of the sludge, okay, sludge or the solid material, comes out. So it's become more thick. Okay, the whole solid becomes more thick. That is the compression. So it's a kind of settling due to the pressure of upper layer on the bottom layer. Okay, so there are two or three layers you can imagine. Like the top layer is actually compressing the bottom layer, and because of that, the water between the voids, like whatever remains in the void between the particles, it goes out and the sludge becomes thickened. So that kind of thickening of sludge is known as compression settling. Okay. So here the compression settling is also shown here. The hindered settling is shown here. Now, which are the units that use this sedimentation or works on sedimentation theory, you can say. So, in raw water or even in water treatment unit, screening is not used in water treatment. Screening is used only in wastewater treatment. Uh, grit chamber is one of the units that also works on sedimentation theory. Grit chamber is used to remove the particles, grit particle, which are heavier than total suspended solid. They are heavier than suspended solid. So they are larger particles, few in size, maybe like more than greater than 1 in size. I think let me just see if the size of this grid particle is given here. I think there should be. Uh, okay. Um, Let me see. I will put that size of the grid particle. Okay. Then sedimentation also works on plain like sedimentation theory, and as I have explained, then sedimentation added with coagulant. So like if the coagulation process is also going on in the tank, then the particle will again settle, like following the sedimentation theory, and maybe flocculent kind of settling may happen. So now, after knowing this is like grid chamber. A very brief description of the grid chamber is given here. So as I said, they are mostly inorganic. I already told you, mostly inorganic particles, grit, sand, gravel. So these are the big particles, bigger than the suspended particle generally. So they are heavy enough and they just settle down very quickly, having subsiding velocity or specific gravity substantially higher than that of organic solid. Okay, they are commonly located after the bar screen. So these chambers are after the bar screen, which we have seen already. The grid chamber is provided to protect the mechanical equipment like pump and all from abrasion, wear and tear, reduce the formation of heavy deposit in pipeline if this grit will remain in water or wastewater. Like when we are disposing the wastewater in river, then this grit will settle down in the pipe and cause a like reduce the efficiency of conveying the water to the river. Okay, so or means you can say it will choke the pipe. So that is why we need to remove the grease. Reduce the frequency of digester cleaning because caused by excessive. So digester, generally sludge digesters are used to thicken the sludge and to dry the sludge, you can say, to even kill the bacteria, to make the sludge free from bacteria, and also to make it thick enough so that they can be disposed of. They will not remain bulky and they can be disposed of easily. Okay, so in case of digester, if there are like large amount of grit would be there, then digester cleaning will means frequent cleaning of digester will be required. Now the three type of grit chambers are horizontal flow, aerated, vortex flow type. Okay, so these are the three type of grit chamber. Okay, vortex flow type means in upward direction, the vortex flow of water will take place, and the heavy grit particles will drop down. It will go down, and the small particle will remain in the water, and it will come out. Then this small suspended particle can be removed in settling tank, primary settling tank also. So these are the three types. So the first one is vortex flow. This is horizontal on the left hand side, and this is the helical flow type, the second one on the right hand side, right? In top bottom two figures you can see. The settling tank, there are two types, like various types. We can define it in a different way. First is like based on the process. Batch process means fill the water and then withdraw the whole water, then again fill the second batch of water, and then after a certain retention time withdraw the clean water, and so on. Then continuous flow type means we are just filling the water and removing like continuously removing a portion of water, and then like so input and output is going on simultaneously. That is like continuous flow type. Then rectangular, based on shape, rectangular, square, and circular type of settling tanks can be there. Based on the flow direction, horizontal flow and vertical. So you can see in the top one is the horizontal flow. The flow from the inlet on the left hand side is going inside in a horizontal direction, and the flow from the right hand side outlet is coming out, and it's like kind of horizontal flow. In the bottom figure is showing the vertical flow type, right? The influent is going up from the bottom of the tank. Okay, so this is vertical flow type. This is how much is the time? What is the time? Oh, we have time. Okay, now now we need to know how much particles or how can be removed in a settling tank, and what is the time, detention time or retention time is required to remove the given amount of particle, you can say. Okay, to achieve the maximum efficiency of particle removal in sedimentation tanks. So the detention time, so you consider the right hand side, there is a figure. Say the height of the tank is h, the width of the tank is b, and length of the tank is l. So b is not shown in this figure, but you can assume that b is perpendicular to the this PPT or this board. Okay, so detention time can be given by, okay, now assumption, we should go through assumption also. The concentration of the suspended particle of each size is same at all the points of vertical cross section at the inlet end. Okay, so concentration, it's a homogeneously mixed water, you can say. Okay, and for each size the same concentration is there, which is an ideal assumption, which is not happen in real situation. A particle is removed when it reaches the bottom of the sea. So it's a simple logic that all the particles which which enter the sedimentation tank with velocity Vh. They will have two velocity components, Vh in horizontal direction and Vv in vertical direction. The resultant velocity will be vector sum of these two velocities, and the particle which will means strike the bottom of the tank, all the particles which will hit the bottom of the tank will be removed. So this is the simple, you can say, logic behind this theory. So therefore, the detention time can be given by volume divided by the flow rate. Volume of the tank divided by the flow rate. Volume would, for a rectangular tank, the volume will be equal to B into L into H upon Q. Okay. For a circular tank, this is the formula for detention time, where D is the diameter of the tank, H is the vertical depth. I already told you B and L are width and length of the tank. Okay, in general, the detention time would be between 4 to 8 hours. for plain sedimentation and 2 to 4 hours for coagulant added sedimentation process. Now, if that theory like which says the velocity means whatever particle is moving inside the tank with VH and VV, they will be removed if they strike the bottom of the tank, then that means that all the particle having the velocity greater than this resultant velocity will settle down. Okay, so here it's saying each discrete particle is moving with horizontal velocity Vh and the downward velocity Vv. The resultant path is given by the vector sum. Okay, that I already told you. Assuming that all particles whose path of travel are above AC, okay, will pass through the basin and from geometry. So all the particle whose like path of entry is above this line AC, means the particles which are not striking on the bottom of the tank will be removed from the tank, and the particles which are below this line AC will be settled down. This is what we can assume. Okay, therefore if we take this in the consideration, then VH, the horizontal velocity divided by vertical velocity component, would be proportional to length of the tank. VH will be proportional to length of the tank and VV would be proportional to height of the tank. Okay, so VH upon VV is equal to L by H. This is like kind of simplification of the whole process which is going inside the tank. So VV can be given by VH into H by L, and VH, which is vertical horizontal velocity, can be given by flow rate Q divided by B into H, right? Horizontal velocity is actually in B, like it can be given by it can be affected by the cross sectional area of the tank. Okay, Q upon BH. So VV is equal to Q upon BL. So this is the velocity. Any particle having vertical velocity greater than Q by BL will settle down. Okay. If the particle is entering the tank at any distance h1, at any height h1, not at h, then the particle having the velocity is greater than h1 upon h into Q by BL will settle down. So it's a simple logic behind to visualize the settling of the particle in a sedimentation tank. So this is another example. You can go through the example. It's already solved example. The two examples are given. Is there any question? Any question? Okay, so if you don't have question, then tomorrow we will have class at 8 because I did not take class on Tuesday. I was traveling that day. So tomorrow I will take class and we can, okay. So we will learn, I think, filtration in tomorrow's class. Okay, so that is all for this class. Thank you. Let me see if I have downloaded the attendance or not. Yes. Yeah. Okay. Okay, bye. I will stop
Hello.
the recording now. Yes.
Ma'am, can you please share the answer key for our quiz? We haven't got it yet.